All right, everybody. We are the League of Young Inventors, and we're so excited to present as part of this global innovation field trip. And this is our session. We're calling it From Play to Physics. So really talking about how young learners can be engineers, and we're really excited to be here. So while we get started, we're going to spend just like 30 to 60 seconds to give you a chance to go and grab a coin. What will work best for our presentation today is something like a larger coin if you have it, something like an American quarter. But really any coin will do. And if you can't find a coin, something that I like to use is just like the lid to this Play-Doh container will work. So like a little lid to a jar or just something. And we'll explain why you need that in just a couple of minutes. And then also if you have like a pen and paper that you can take some notes, that'd be great. That's totally optional. You don't have to have that. And while we wait for everybody to do that, Indy and I will just tell a little bit more about ourselves. We did a little introduction, but we'll just do it again. So like I said earlier, my name is Mallory Schmidt. I'm actually the program manager for the League of Young Inventors. I was a former classroom teacher. I taught STEM classes for preschool students up through 6th grade students. And so have really enjoyed doing some of this like hands-on learning with young learners.
And like I said, I'm India Williams. I'm the Director of Content and Media at the League of Young Inventors, and I've been with the League since 2019, so quite a few years now. My background is in art, but I've also worked with kids for well over 10 years and taught English abroad, so in Cambodia and France. So yeah, I'm just really excited to be here today and to share our work with you all. Mallory, should we just keep it going?
Yeah, let's do it. You guys will
Perfect.
still have a few more minutes if you're still looking for those items, but we're just going to keep chatting for a couple minutes. All right, so we are the League of Young Inventors, and we are a national nonprofit that really believes that children have the most fun learning and learn the most through hands-on exploration and building. So we've developed some different curriculum kits, some hands-on curriculum kits and units that really engage even our youngest learners. So talking as young as kindergarten, so 5 or 6 years old, in engineering design and the science and engineering practices. And so when you work with us, or what we offer is some different things. So we have slide-based materials kits or slide-based lessons. So think like Google Slides that are very interactive. We'll kind of show you what those look like in just a minute. Some materials kits, and then some worksheets to really help students and teachers as they're going through units. And each of our units are anywhere from 10 to about 15 hours of hands-on, playful, exciting activities. So you can see different things like spinning tops and paddle boats and puppets and lots of different fun, exciting things. And so I'm going to just let you see some of this in action through this video. Go ahead, India. And so what you see first is our spinning tops. We're going to spend a little bit of time looking at those spinning tops in just a few minutes, but really that encourages creativity and testing using everyday materials. And then we have our floating boats, which really introduces some water-based testing and some hands-on experimentation. You just see how excited some of these students are getting because their boats are floating, right? And then we have our balancing mobiles unit, which we say is really good for those young learners because they're learning how to twist and assemble different things. So they're learning how to utilize fine motor skills. And then our rubber band paddle boats, which really challenges students to go back and look at their design. So if we're thinking about that engineering design process, getting to iterate and go back to their designs to make changes as they need them. And then our marble runs unit, which is a really exciting and fun way for students to start with some simple models that really go back into some much more elaborate final designs as we start to talk about the science and engineering behind what they're doing.
Okay, so I will jump in. So we're really excited to show you how we kind of engage kids as young and as kindergarten, as Mallory mentioned, in the engineering design process. So what is our version, or what is the engineering design process? Well, it's a series of steps that inventors and engineers follow to come up with solutions to real problems, right? And I'll just quickly walk you through our version of the engineering design process. So it always starts with identifying the problem. Then we jump into this research step, which I'm going to go into more detail about in just a second. After research, we brainstorm. So that's, sketching and designing and choosing materials to build your solution with. Then build. Once we have our first build, we're going to test and evaluate that build and have a chance to redesign it and make it even better before sharing and reflecting on the whole process. So I'm just going to jump back to that research phase. So often, when students are presented with a real world problem to solve in, let's say, a classroom STEM activity setting or design thinking, things like that, they're often asked to jump right into brainstorming and building solutions, even if they don't have the experience or the skills to do so. So often this can cause a lot of overwhelm and frustration for kids, especially if they're not used to this process, if they're not used to hands-on learning. So we added this research phase where students spend 4 lessons diving into open-ended experiments and guided model building. And during these 4 lessons, students are able to develop a strong foundation of maker skills. So things as simple as making sure that everyone knows how to rip tape and cut paper and make folds for some of those younger kids, and those get more complex for the older grades, obviously. But making sure that before kids are coming up with solutions, that they all have uh, the background knowledge of how to build, right? It also makes sure that they have a deep understanding of the science concepts at play. So they're really seeing those in action, and they can design their solution with all of that in mind. And finally, they get comfortable with embracing failure as learning, which really helps when creating your own solutions to come to real world problems. So, yeah, once it's time to brainstorm, they're well equipped to design and build an awesome solution to the problem at hand. So, now let's take a look. Let's take a closer look into the research phase. So, I'm going to pretend that everyone is a student, and I'm going to walk you through lesson 1 of spinning tops. Okay. So, this is where you're going to need that coin or lid or round circle object. Okay, everyone, welcome to the League of Young Inventors. What is an inventor? Well, an inventor is someone who uses their creativity and their knowledge to make new things. Anyone can be an inventor, even kids. So we're going to join the League of Young Inventors to help them solve a problem. Let's take a look at this clip on screen. This clip comes from my friend's workshop. My friend is a toy engineer. And recently she started a new project, but something's not working quite right. Let's just take a second to silently observe this video clip. What do you see and what do you wonder? Let's keep those in mind as we investigate a little bit more. And feel free to drop your observations in the chat if anyone wants to. Mallory will will take a look at those. So, does anyone recognize the toy in this image? Anyone? So it is a toy top, right? And what is this top doing? Well, it's spinning, right? Tops spin around and around. So what actually is a top? A top is a toy that spins around its axis. And the axis is that invisible line down the middle that it rotates around as it spins. I'm going to play a part of this video that shows lots of different types of tops from around the world. So let's just take a little look. And take notice of the different types of materials that are being used here. The different sizes and shapes. You can even use things that were not designed to be tops as tops, like a jack or a thumbtack even. Pretty cool, huh? Okay. So let's think about when tops might have been invented. What do you guys think? When were the first tops invented? 100 years ago, maybe 500, maybe 1,000? You can drop your ideas in the chat. Well, I'll give you a hint. Tops are actually among the earliest toys ever made, and they were found in almost every single part of the world throughout history. And you can see this top that's in the white square right here. That was actually found in King Tut's tomb. So children have been playing with tops for thousands of years. So now that we know a little bit more about tops, let's go back to my friend, the toy engineer's workshop. What do you notice? Well, obviously the toy engineer made a toy top, but it's not working quite right. Something's off. What's going on? Well, the top doesn't spin for very long. It kind of just wobbles and falls over really quickly, right? So our mission now is to help the toy engineer solve the problem by engineering our own spinning top toys that spin for at least 5 seconds. To solve this problem, we are going to go through the engineering design process, which we just talked about a second ago. So it's the series of steps that inventors and engineers use to solve problems. And we actually just completed the first step of identifying the problem. So we're going to go into research now. So you see a washer on screen, but this is where we're going to grab a coin. Anytime you see a washer, that's what students would use in the classroom, but we can use our coins. So if anyone has their coin in front of them, try standing it on its side on the desk or table or wherever you are. Think about what's going on and what do you notice? Is it easy to stand it on its side? Is it tricky? Okay. So yeah, what happened? It's pretty tough to stand a coin on its side, right? It's a little wobbly. It doesn't stand up easily, right? And that's because only that tiny part of the coin is touching the table. You could say that it's difficult to balance, right? So the coins were unbalanced. What does an object that is balanced look like? Well, when something's balanced, it stays steady and straight. It doesn't tip over to one side. What causes the coin to tip over? Well, there's a force that many of us probably know that is actually what causes it to tip. To tip over, if anyone has a guess, they can throw it in the chat of what that force is called. I'll give you guys like 5 seconds. 3, 2, 1. Okay. So it is gravity, right? Uh, I'm sure we've all heard of gravity. And gravity is that force that pulls all things down towards the earth. That's why when you jump, you land right back on the ground. When the coin tips over, it's because of gravity. What if we could find a way to get the coin to balance standing up? I bet if we spun it, we might be able to get it to stand up for a longer time. Let's watch this quick video to learn how to spin the washer. This is just a technique that makes it a little bit easier for students.
Let's learn how to spin a washer. Grab the washer with both hands. You'll use your pointer fingers and thumbs to hold the washer and spin. Let's watch that in slow motion. It'll take some practice, but once you get the hang of it, count. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi while your washer is spinning. Then record your results on your worksheet. Give it a few tries and circle your best time.
Okay, so if anyone wants to take, we're gonna keep moving on, but as we move on, if you guys want to try spinning and counting and recording your results on a piece of paper, it's a pretty fun activity. So you can test out this process of spinning the coin. Okay. So when we spun the coin, what happened? If gravity pulls things down, what helped the coin stay upright? Well, the spinning it helps the coin to resist the pull of gravity. But when the spinning slows down, gravity wins and the coin eventually falls over. Why do you think we're spinning coins when we're talking about tops? Well, it's because coins spin and balance in the same exact way that spinning tops do. It's the same process. Now, let's look back really quickly at my friend's workshop. What do you notice about the top as it spins? Is that balanced or is it unbalanced? Right. It's unbalanced for sure. It's just wobbling and hitting the table. So let's think, how could we apply what we just learned about the top to kind of help us make some notes on how we could solve this problem? So if you guys want to write that down or throw it in the chat. And I am going to pass it back to Mallory now, and she is going to walk you through just a quick overview of the rest of the engineering design process. And yeah, thank you guys so much for jumping into lesson 1 with me. Mallory, you could take it from here.
Yeah, awesome. Thanks, India. So we kind of gave you a preview of what we talk about with students as we go through some of these units. And I'm just going to talk to you about what would happen next if we were actually in a classroom together getting to go through some of these units. So now that we've talked a little bit about tops and the history of tops and we've identified a problem, what we found is that there's a lot of kids, and maybe you guys on this call as well, have never actually played with a toy top. And so in lesson 2, we really ask students to just get to play with some toy tops, right? And get to do exactly what we just did, making some observations, collecting data on these different styles of tops, exploring how they spin and getting excited about what's to come. And they get to collaborate with others because they're going to work in pairs together as they go through this. And then in lesson 3, we're going to follow a series of steps supported by those maker videos, like India showed us the video on how to turn a top. So we have lots of those little videos kind of embedded throughout the lesson for students to construct the same basic model of a toy top, really asking them just to kind of all follow the same steps so that we can make, again, some more observations. And through this investigation, what we really want students to learn is that heavier objects tend to spin for a longer amount of time, because we're going to need that when we go to make our own top at the end. And then in lesson 4, which is the final lesson in our research phase, students get to explore 2 key variables, which is the placement of added weight to their top and the shape of the top's body, really investigating that balance and symmetry and how they influence the spinning time of their top. And we like to connect it to real world things. So you see on your screen the spinning ice skater who's pulling her weight close to her body or extending it outward, really showing how this phenomenon applies to everyday life.
We can skip this.
Yeah.
Right? Just 1 second, let me get.
Not all of the students are coming to the classroom on the same playing field, right? So they have different life experiences. So it really hones it.
Sorry, guys, I'm just going to skip this part really quick. Okay, we're back on track. Sorry about that.
Perfect. After our research phase, we get to go into the origination phase, which tends to be everybody's favorite, right? Because you get to do some brainstorming and building, you get to create something, you get to test and evaluate it and redesign it. So that is after our research phase, because we want to make sure that you're really informed and that students are really informed with what they're doing and they're not just making some guesses, right? So we just did a ton of research and found out a lot of science to back up what we're going to do next. So in lesson 5, during the brainstorm phase, students get to review different criteria that they're going to need. So the goals of what they need to know to create that successful toy top. They'll get to explore some new materials that they'll have available for building. And they also get to consider a social aspect of their toy design and try and figure out and brainstorm some special features to make their top fun for other kids. And they get to sketch their design and shop for materials to bring their ideas to life, because in lesson 6 is when we get to start building our designs that we sketched in the previous lesson. And our goal is really to allow students to express their creativity through their own process of construction. So you can see those 2 different tops, or those tops that all of those students are working with, all look a little bit different, right? Because they get to bring their own personality and creativity to their toy top. And then in lesson 7, we actually don't bring out any building materials. So we only want students to play with just their toy tops so they can really focus on conducting their first official test of their toy top and recording their observations. They get to evaluate whether or not their top met the criteria it needed to meet. And then finally, with their teacher, they get to review all of those key learnings from the research phase. So thinking about the balance and symmetry and all of that, so that they can go back and refine and improve their designs. So in lesson 8, we're going to use our plans from lesson 7 to complete the final construction of our toy top. So we went back and we checked the criteria that we need to meet, maybe made some changes to our sketches, and now we get to make a final design to present to our class. Because in lesson 9, which is our final lesson, students get to focus on that communication and celebration. They get to prepare and deliver a presentation about their final design, really reflecting on the evolution of their top and the lessons that they learned. And then they could potentially make a poster advertisement highlighting their special feature that they decided for their toy top to make it fun for other kids. And then we like to just make some career connections to some different potential careers that students might enjoy, or students might want to look at, who enjoyed doing this activity, building something that's fun. And then, of course, we like to make some literary connections for students. So offering some different optional stories that they could read that might get them more interested in some inventing and innovation. And then just really quickly, just to show everybody, we talked to you a lot about spinning tops, but that's not the only thing that we offer. And so we have things on balancing mobiles and marble runs, building bridges in neighborhoods. So our toy invention series really asks students to design and create their own toys, applying scientific principles in a really fun, hands-on way. And then our everyday engineering series, which challenges students to tackle real-world problems, really building some critical thinking and adaptability skills, talking about community and local problem solving, and really understanding how things in their community work. And all of our units really integrate some science, some ELA, some math, computational thinking, and social studies as we do that. And then to wrap it up, all of our units provide about 10 to 15 hours of hands-on STEM learning and joy. We teach those science and engineering practices in the 4 C's, so critical thinking, creativity, collaboration, and communication. We really use everyday materials, so no special equipment, nothing super high tech. We try and make it as easy as possible for students, and it can be taught really by any educator in the classroom. And then at the end, just a little bit about us, our emails, and then we'll open it up for some questions.
Yeah.
So can I start?
Yeah.
Yes.
So congratulations, first of all. I'm an inventor. I'm a science and inventor. And when I see initiatives like that to put in the kids and the teenagers this idea about inventions, about solving problems, I feel very excited. I'd like to know, how did you come up with this idea? What was the biggest motivation factor that made you to jump in this project?
So I worked very closely with our founder, Megan Eisen, from the beginning of when this started. And I think one of the reasons why she started this is that she saw that her kids they were in 3 different types of schools, and they were only getting 45 minutes of science per week. And in those 45 minutes, there was very little opportunity for hands-on learning. There wasn't a lot of experimentation. It was a very traditional approach. So I think that just really inspired her to start this journey. And we started out as a maker space. We were an after-school program where we were testing out these projects and really refining them. so that we could eventually kind of develop our own curriculum that was taught in schools across the country and even hopefully one day the world. So yeah, I think that's where it kind of started. But I don't know, Mallory, what makes you passionate about STEM or this project?
Yeah, not necessarily this project, but all of our projects really I love. But I loved teaching STEM because I felt like that was an entry point that I didn't get as a student. So I always joke and say, had I got to experience science in a really hands-on way, that I might have actually become an engineer because I love doing it. But science was not my strong suit when I was going through K-12. And I think because I'm just a much more hands-on learner. So that was kind of my journey into teaching STEM and why I've loved getting to help kind of develop and get teachers excited about this kind of learning, because it really is fun to see kids get that spark that they might not have gotten in a traditional science classroom.
India and Mallory, if I can just jump in for a second.
Sure.
My name is Jake Mendelson. I'm an engineer and I'm also an educator. And I think what you're doing is absolutely excellent. And the way that you're doing it is even more excellent. As an educator, I've run into many situations where the traditional education says, no, science has to have a graph and it has to have a formula and it has to have mathematics. And that's eventually it will. But what you're doing is you're setting a spark within these kids. And then later, when they get to the traditional science, they can learn the formula and find out why the spinning top doesn't fall over, but a stationary top does. There's actually real science, but the first thing they need is a spark. And what you're doing is absolutely excellent. Thank you.
Of course.
Thank you so much. That's so wonderful to hear. Really appreciate it. Yeah.
Just remember, I don't know if you already are, but you may be getting pushback from traditional educational systems where they say, no, this isn't STEM. There isn't a mathematical formula. There isn't a graph. There isn't, and that's nonsense. But I don't know if
Yeah,
you're having
it's,
that trouble.
finding our that sweet spot of where we fit into the school day is something that we're constantly kind of maneuvering, right? So it tends to be more on the supplemental side, but any way that we can get in there, whether it's, we even have alignment to ELA and connecting it that way so that we can get these, get more kids to have access to this type of learning. We're all for it.
Great, great. Well, unfortunately, we have to go now. Your time is up. We have another great presentation, but I just want you to get all the compliments you can possibly get because I think you're doing a wonderful job. Thank you.
Well, thanks so
Thank
much.
you so much. So great to meet all of you.